Good evening, everyone.
Good evening. Yeah, good evening.
Okay, nice. All right. So, is everybody ready? Should we get started?
Yeah, sure.
Okay, great. And as you all already know, this lecture is going to be about function equations and the basics of function equations. My job here is not to actually give you well-written solutions. I'll try to motivate most of the stuff that I explain here. So, motivation and ideas over formal solutions. I'll probably leave a lot of details to you guys, but I guess that's important because that way you learn more of diligence. Without further ado, let's get started. So, the basic idea in any functional equation related question is that we're given an equation, maybe some more constraints, and our job is to prove something related to that function or maybe find such functions. Before we actually get to any of the basics, one thing I like to say is that you should probably not think of functions as polynomials. Like, polynomials are a bit different and behave a lot more predictably and nicely, while functions are just any sort of a relation. Like I could be mapping any input to any other output and it would still be a function. Let's say, for example, I had the integers, right? And so I could map all the negative integers to, let's say, -3 and 0 to 0 and any positive integer to 327. And this is a function. This is a well-defined, very nice function. And so I don't want you to think of this as the weird stuff because this is the normal stuff. This is how functions usually are. And this is actually just a better and more free way to think about them. Right. Now we'll just get started with the numbers and basically these are all the different domains and inputs and codomains that we could encounter during a functional equation problem. Naturally, the first and most important number here is 0. Zeros are good as images, zeros are good as inputs. What I mean by that, oh, and before that, I'll just clarify. I'll be using the same terminology as in polynomials. And what I mean by that is I'll say z is the root of f if f of z is 0. Alright? And 0 is, as I said, roots are good to look at, and 0 as an input is great because of all the various properties that we know about 0. And then you have the naturals, which, for the record, natural numbers, the functional equations which are over natural numbers, tend to have a lot of number theory in them and have a number theoretic flavor. We're not going to be covering those today. We're actually just going to go over the more classical ones, which are over the rationals and the reals and like inputs and that kind of stuff. That's what we're going to work with. Similar thing holds for integers. Then after this, we have the cooler numbers, or I think they're pretty cool. The rational numbers. The thing about rational numbers is that they're super nice, and for various reasons. Like for one, you could get for whatever size you wanted, you could
You
get.
don't think natural numbers are cool?
I think natural numbers are pretty cool too, but for the sake of our lecture, I'm not gonna be thinking they're cool just because I'm not.
Yeah, they are quite complicated. Bit complicated, yeah.
Number theory is hard, at least to me. I think algebra is a bit easier in that regard. So that's why. Natural numbers are also cool.
Yeah, okay.
Numbers are very cool as well. Okay. And the reason why I think rationals are cool is because rationals are a lot in number and you have a lot more freedom with them. Like, for example, you have the freedom with real numbers, right? You could pick almost anything anywhere. But at the same time, rational numbers also preserve that sort of divisibility and squares and those sort of primes and relations which the natural numbers and integers have, which is why they're like the best of the both worlds, which makes them very convenient to work with. Another cool thing about rational numbers, which I'll just highlight really quick, is that For any real number, you could get arbitrarily good approximations for that real number. What do I mean by this? Let's say you have the real number square root of 2. Now, this is not a rational number, but for example, I could write numbers, rational numbers like 1.4, 1.41, 1.414, and so on and so forth. And each time I do this, I get a better approximation for that irrational number, which is square root of 2, even though these numbers are rational. So you could technically think of these as an infinite sequence of rational numbers which tend towards that irrational number. And if you have any sort of continuity, any notion of continuity or size or increasing in any function equation, and you know how to deal with rationals, then this actually becomes a very cool tool. And now I'll just quickly mention a few of the properties that we'll be using almost all the time, which are injectivity, subjectivity, bijectivity, and involutions. Okay, first off, injectivity. Injectivity is basically an equivalence relation. What do I mean by that? What it means is one thing implies the other, and the other thing implies the first thing. If one of them is true, then the other one is true as well. For example, what injectivity says is if f of a equals f of b holds, then a equal to b holds as well. If the images are equal, then the inputs are equal as well. For example, the function I had defined earlier was not an injective one because let's say f of 1 and f of 2 were both 327, right? So that was not an injective function. On the other hand, let's say f of x equal to x plus 1 is an injective function. Why? Because if two values are equal, then you get a plus 1 equal to b plus 1, which implies a equal to b. Is this clear?
Yes, sir.
Not clear.
Great. Now, a bit less common, but still very useful nonetheless, is surjectivity. What surjectivity says is that for any element in the codomain is where the images lie. For any element in codomain, you could find some input in the domain which gives that image. Let's say you picked some element y, which is in codomain. Then you could pick some x in the domain such that f of x equals y. And this holds true for any y in the codomain. For example, the most trivial example, f of x equals x, i.e. the identity function is a surjective function over any domain. Because let's say you had the real numbers, then you could pick any real number and then f of that real number. Well, this is sort of hard to explain, but I hope you get the point.
Yeah,
And
that's because 2 is equal to 2 and not equal to any other real number.
exactly. And so that's why f of x equal to x is surjective. Similarly, almost any linear function over the reals is surjective. And then you have bijective functions, which are basically functions which are both injective and surjective, which makes them very cool and nice and good to work with. And it's also because injectivity is such a powerful tool anyways. We'll see an example or two of this later. Finally, one more property, which is involutions. Now, involution basically says this equation. If you have a function, any domain, any codomain, we don't care, but if f of x is x, then f is an involution. All right? Gosh, why is everybody so silent? Anyways, the nice thing about involutions is that they're both injective and surjective. I think that's very easy to see because if you had f of a equals f of b, then you could just apply f on both sides again, and that would give you f of a equal to f of b. But by the first equation, you get a equal to b. And then like if you just look at this equation, you could set x to be any real number or any number in the domain, and then this equation is satisfied, from which we see that f is surjective as well. So involutions are both injective and surjective. Okay, I guess that's enough theory for us to get started now. And naturally, our first
Yeah,
function equation. Sorry?
yeah, let's get started with the examples.
Yes. So the first example that we're going to go over is probably the most simple one, yet it's also very important. That is Cauchy's functional equation over the rationals. First things first, if you directly try to attack this problem
Okay, okay, over the rationals. Okay. I mean, real.
yes,
I thought real.
over the reals, it's a bit more complicated because you could have pathological solutions. The reason for that is a bit more interesting and certainly beyond the scope of this lecture. We could certainly cover it
Yeah.
sometime in the future though.
Okay. Okay.
The reason for that is because over the reals you have things that don't really talk to each other. That's sort of hard to explain, but whatever. In the rationals, you have a very good structure, similar to the similar to that of the integers. Okay, as I was saying, if you directly try to attack this problem over the rationals, you'll probably not get anywhere. So our best bet is to just take make things simpler, take a step back, and try to solve it over the naturals or the integers first. And when we're trying to do that, f of, I mean, just f of 0 equal to 0 is super apparent if you just plug in x equal to y equal to 0. Does everybody agree with this?
Yes, sir.
Because you get 2 f of 0 equal to f of 0, which implies f of 0 equal to 0. So with that out of the way, on the integers, the smallest number in value that you have is f of 1, right? I mean, the input is 1. And so for what I'm trying to say here is you cannot really hope to get any information about f of 1 just because of how the integers are. So we might as well take f of 1 equal to c for now because we know that this is the smallest possible integer in size, and so
So
there's no.
we are
Yeah,
first trying to solve this on natural numbers.
yes, natural numbers and
Okay.
integers as well, but of course natural numbers first. Why? Because
So
as I
we
said,
assume f of 1 equals c, but if that does not exist, like f of 1, we know f of 1 exists or not. We have
we
assumed that f of 1 exists. So
no,
and we take.
actually, look at this. Look at this bit here. The function is from the
Okay.
rationals to the rationals, and what that means is if you plug in any rational number for the input, its image is going to exist.
Is this clear by the equation?
Yes, it's not clear by the equation. It's actually clear by this thing here. Like, look at this. Do you see my mouse?
Yeah, yeah.
Yeah, it's clear due to this. What it says is the function goes from q to q. It takes some number in the rationals and throws out another rational number. And so what this means is you could plug in any rational number that you want and it's going to work out.
Yeah, that's right. My question was that will it also spit out some value for f of 1 also? Because
Yes,
sometimes
because
some functions are not defined on some inputs.
it,
Okay.
yeah, go ahead.
So
Uh,
that's why I asked this question. That we are assuming f of 1 exists, and we are
no,
assuming that. I
like
see.
no, it's like defined from Q to Q. So that means like one f of one is defined. But if f of one is
Okay.
defined, it's defined in Q. F of one
Okay.
is a rational by definition.
Yes.
Yeah.
1 equals
Yeah.
1 by 1. So if
So,
1
so,
is
so that means in any problems like this, we can just if we are given the domain and range, then we can assume for some value that it exists
no,
without
in,
any.
for all that
I am you're not audible.
Yeah,
am I audible now?
Yeah, yes.
Yeah,
Okay, exactly. As someone in the chat said, if you plug in anything from the domain, an image is guaranteed to exist. For example, I may or may not have f of square root of 2 defined. As a matter of fact, in this case, f of square root of 2 is not defined. And the reason for that is simple. Because our
yeah,
domain
because it's not rational number.
exactly. On the other hand, let's say you had taken 2, or I don't know, you had taken 29, because 29 is a rational number. Any integer is a rational number, any natural number is a rational number. Why? Because you could just say, the rational number is like an integer over another integer, right? And for any integer z, you could just say z equals z by 1, right? Because 1 is the identity. And so
Yeah,
any
got it.
integer,
Now understood. Thanks.
yes, nice. Okay. And as I said, because 1 is the smallest one in value, we don't really hope to get anything involving 1. So we might as well assume f of 1 equal to c for now. And let's see what we get out of it. First thing we see is that you could just say 1 plus 1, or f of 2 equals f of 1 plus 1 equals f of 1 plus f of 1. And here I'm just using the given definition. And more like I'm just plugging in 1 for x and 1 for y. And that gives you this. And by definition, or I mean by the constant that we just defined, this is 2c. All right? Is this clear to everybody?
Yeah, quite clear.
Yeah.
Yeah.
Okay. Then you have f of 3, which you could write as f of 2 plus 1, which by definition again is f of 2 plus f of 1, which we get is 2c plus c equal to 3c. And blah blah blah, f of 4 equals to 2 plus 2 equal to 2c plus 2c equal to 4c. Do you guys see a pattern here? For any natural number, you could just say f of n equals f of n minus a. Oh, there's this plus a, where a is any other smaller natural number, and you get this. Is this fine with everybody?
Yes, sir.
Right. And so what we see now is for any natural number, you have f of n equals nc. This is the key takeaway here. N equals nc, where c is f of 1. All right. And then you could do a similar thing for the negative integers. And from that, you basically get for any z in z, f of z equals zc. All right. With this,
Um,
by the, huh?
yeah, clear.
Yeah, yeah. By taking a step back now, we've actually gained a better understanding of the problem, and we also know how it behaves over the integers. So our next goal now is to try to find the value or try to figure out what's going on over the rationals. And I guess the most intuitive and obvious way to do it is if you could take two rational numbers x and y such that their sum was an integer, then on one side you'll have an integer and you know how integers work. On the other side you have rational numbers, so you'll get some information about rational numbers as well, right? And so after this, the most natural guess, or at least in my opinion, is x equal to y equal to 1 by 2. And what does that give you? That gives you f of 1 equals f of 1 by 2 plus f of 1 by 2. What this means is f of 1 by 2 equals f of 1, 2. Is this clear to everyone?
Yeah, clear.
Yes, sir.
Yeah. And so now you see this, and basically the rest of the idea, I mean, the idea for any normal rational number is very clear now, right? For example, what you could just do is you could take f of p by q, where p by q is the rational number, and then For that, to find this, what you say is you say f of p equals f of p by q plus f of p by q plus blah, 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 plus f of p by q, where this sum is how many times? It's q times, right? And this. You know what this is because this is just p. And so you obtain f of, I mean, this is Cp, my bad. So you obtain f of p by q equals f of 1 times p by q. And so the problem is solved. And the solution is just f of x equals f of 1 times x. And with that, our first example is done. Now, this might seem like a very trivial or basic example, but the reason I decided to include this is because there is one important underlying idea here, and that is to, if you're stuck initially somewhere and you don't seem to be making progress, it is often important to take a step back, make things simpler, or look at it from a different perspective or take a new approach. Here, if you have tried for the on directly for the rationals, you may or may not have solved that quickly. But by falling back to the integers, which had an easier structure to work with, you could actually gain a better understanding of the problem. And after that, you were able to solve it quite quickly. Is everybody clear with this example now?
Yes, sir.
Yeah, quite clear.
Yes.
Okay, great. I'll just answer this. Okay, before we actually get to this example, I'll just like to ask you guys one simple question. What happens, I mean, just consider this expression, f of x. If you replaced x by, let's say, f of x, what do you get?
We get that f is surjective.
No, no, no. I said this innermost x, if I replace that by this term, what do I
Ah,
get?
um, f of x plus 1 equal to f of x plus 1.
No, just ignore the equation for now. Okay, my bad. Just ignore the equation for now.
F of x. So
Okay?
that is f of x.
Yes, exactly. I'll
Triple.
just triple. Exactly. Now, again, in this same expression, what if I just let this be
So I
an
think we can
in?
use two times
Huh?
the same thing. We can use, I think we evaluate three times and then use the same thing twice.
Yeah, but very quickly, if I just took f of this whole thing, like this whole expression, if I took f of it, I just
Yeah,
Yes,
I just took this expression and I put it and I threw it into f, and I get this. Is this clear?
yeah, yeah, clear.
yes, sir.
Right. What? Why did I do this? What motivates this? The reason is actually very simple. We get this expression, but this expression is expressed in two different ways. But it's the same expression, and this will be equal to something, and this will be equal to something else, and so you deduce that something equals something else, right? And you get this new equality out of this. And the reason for that is you just want to exploit iterations because f of I mean, you could replace the input or you could just take f of that whole thing. And so you exploit the structure of iterations, and by iteration just means repetitive f, like f of f of f of f of. And so you just do that and you exploit that and you get something of this form. And now to clarify this idea, we're just gonna have a look at this quick question. Would you guys like to try it on your own first?
Yeah, sure.
Yes.
Let me know if anybody makes some progress.
I got n f of n equal to n minus 1 plus f of 1 for all natural.
Yeah, that is correct. That is absolutely correct.
We just
You
get
get
Cauchy.
it's not exactly Cauchy because you don't have f of 1 here. If you had f of 1 here, then it would have been Cauchy in fact. But you have f of, you just have 1, right? Is everybody clear with this? How we get this? You just take f of this thing and you get f of x plus 1. And if you replace x by f of x, you get f of x plus 1. And both of them are equal to f of x. And so you get this equality, which holds for all integers. All right?
Yeah.
Yeah. But the issue now is, if what this basically tells us is, if you assume just one value, you get f of x equals x plus c for some c. Actually, it's 1, but whatever. So now, if you plug in any linear function back in here, the issue is that 1 is odd. And so, let's say you had plugged in ax plus b, and then what you get is a equals 1 because the coefficient of x on the right hand side is 1. And that would imply b is either, that would imply b equals 1/2. But the issue with that is 1/2 is not an integer. So f would no longer be from integers to integers. And so the answer is no such function exists. So this was just a cute little application of
Yeah.
the triple involution trick as it's popularly known.
Yes, sir.
Yes. Now a much more important trick, or it's not really a trick actually, it's still a very motivated idea. I didn't want to call these things tricks just because in themselves they are very motivated. It's just that their names have the words tricks in them. Anyways, so this one here is cancellation trick. Now, usually when all the terms, okay, what I mean by wrapped, when I say something is wrapped, I mean it is inside of an f, like f of something. Then that something is wrapped in an f, all right? And so with this equation where everything is wrapped, you I mean, it will be a lot harder for us to make progress directly since this is over R. And anyways, what this sort of motivates is, what you see first off is that the last term is sort of y free. And by y free, I mean it just does not have any y in it. And so if you could do something to just these two terms alone, then you might be able to get some information regarding the third term, right?
Can you like elaborate the previous problem again?
Do you mean this example?
Yes, this one.
Okay, okay, sure. So what we did here was you have this equation, right? Just okay, 1 second. You have this equation. What you do is you first off take f on both the sides, like that, right? So what I just did was I took f on both the sides because obviously, right? If the inputs are the same, then the images must be the same too. So this equality would still hold, right?
Yeah. Quite right.
And if place this x. Basically, instead of assuming that my input was x, I chose my integers, so I can totally do that because f of x is also an integer. And so when I do that, I get that and that. And now I guess you can kind of see what's happening because look at these two terms. Like they're the same, right? And so from that you see right here. So this term and this term are the exact same, but the right hand sides are not. But just because these two are equal, you must have that these two are equal as well, right?
Yeah.
This is just like saying A equal to B and B equal to C. So A equal to C. Like
No,
this is all.
I
Hmm?
no, I understood this, but I didn't get the finish.
Okay. The finish is right from here. What you get is because right, I should have mentioned this. Basically, f is defined over the integers, and you get that the difference between two consecutive images, I mean, the images of two consecutive inputs is constant. And over the integers, this is enough to imply that f is a linear function. Like by linear, of course, I mean a line sort of function, like ax plus b form, right? Just try to prove this as a homework. Why this implies that f must be linear. All right. And so once you get this, then you try plugging in ax plus b into here. Like you just assume, fine, f we get f is linear, and then I'll just assume f of x equals ax plus b. And then I plug this into this equation and then just match coefficients. Because you know that whatever the coefficient of x on the left hand side is, it must match whatever is on the right hand side. And so by matching coefficients, you get stuff, and what you get is that f, basically you get f of x equals x plus 1 by 2, if I'm not wrong. And the issue with that is 1 by 2 is not an integer. And if 1 by 2 is not an integer, then this condition is violated. Because we were told that all the images must be equal. And so if this condition is violated, because while doing all of these steps, we assume that such a function exists. So a contradiction. Because function in the first place.
Yeah, we
Okay,
actually see to 1 by 2, but still we must have assumed something incorrect.
exactly. And since this must have existed somewhere, this example is actually of huge importance because it explains or it is an example of something very, very important which shows up way too often as a matter of fact. It's used in almost every single problem that I can think of. And right, and we'll just get to it and I'll explain and I'll try to motivate what that thing is. Right? Just looking at the equation, first of all, we see that the entire equation is wrapped, no free variables. And I'll get to the importance of free variables in a later example, but usually free variables are very, very, very nice. Like the issue with wrapped functional equations is that let's say you knew the solution to not this equation but to some general functional equation, some other functional equation was f of x. But if everything was wrapped inside F's, how will you get this F? It's not that direct or straightforward anymore, right? Because everything is inside of an F, and you want a free variable now in your solution. Which is why wrapped equations are a bit more tricky as compared to normal functional equations where you have free variables. Right, coming back to this example, we see that the third term in this equation does not have a y input in it. And why is that nice? And why is that nice? Because if you could, like, intuitively, if you could do something to just this term and just this term by, let's say, manipulating the y input somehow, then you'll get some information about this third term, right?
right?
Yeah.
Yeah. And then, like, naturally, the most obvious guess that we have is what happens if we just set the two inputs equal, right? That wouldn't affect x because you have a y and 2y here. So you can just solve and get x squared minus x to the 27 equal to y. What I just did was like, I just straight up set x squared plus y equal to x to the 27 plus 2y. Oops. Right. I just did this for the sake of it because I have no other idea. Like I intuitively know that I need to do something about the first term and the second term so that I can get something for the third term, some information about the third term. But then I don't know what to do. So I'll just do the dumbest thing possible and I'll set these two inputs equal in hopes that that would do something. And indeed, you get this y input. And what does this y input symbolize? This says that if I plug y equal to this, then this input, x squared plus y, and this input will be the same, right? Because you get 2x squared here, and you get 2x squared here. And why is this and why is this nice? Because without doing anything to the first terms, you've gotten, I'll just call it a for now, f of a equals f of a plus f of x to the 4th, where x is any real number, like absolutely any real number. And what does this imply? It implies that f of x implies that f of x to the
We plug for y the value we get, and that will cancel.
yes, that will cause this term and this term to cancel because their inputs are the same, right?
Yeah, yeah.
Yeah.
Yeah. And so you get that f of x to the 4 equals 0. But we had placed no restriction on x whatsoever. And so we are forced to deduce that this holds for absolutely any y. And note that this is a perfect square, right? And over the reals, you can just, over the positive reals, you can just take the square root of anything. So we just get that f of x, oops, right? And so from this, you just get f of x equals 0, where x is greater than or equal to 0.
Yeah, I guess because all the any real number can be written
Any,
in fourth root of
yes.
another real number.
Exactly. This holds true for the positives, right? You could take the fourth root of any positive real number and it will still be a real number, right?
Yeah.
But and so we get that whenever x is non-negative, you get that f of x is 0. And so that is great information. Now what do we do? Now the easiest way for us to proceed is to just simply set y equal to 0. Why? Because there you have an x squared term here and you have an even term here, but you already know the last term is 0. And so just by setting the y equal to 0, you get the left hand side as 0 as well. What does that actually give us? That gives us f of x to the 27 equals 0. And naturally, because 27 is odd, you can take the 27th root of any real number as such, right?
Yeah, yeah,
Oh wait, what did I scroll? Sorry. Yeah. And so from this you just get that f of x must be 0 for all the real numbers.
yeah. Because 27th root can be negative also.
Exactly, exactly. Perfectly said.
This was easy for the real numbers, but if it would have a natural number, then things
Yeah.
could have get quite interesting.
Yeah, that would have been a lot more messy. But my job here was to just illustrate the very simple but important idea of stupidly setting things equal to each other so that they cancel out.
Yeah,
And it's simple, right? I mean, it's like you could just say you have the popular saying, right? The more the merrier. In this case, it's the exact opposite. The fewer the merrier. The fewer terms that you have, the more solid information and more concrete information you'll have, and it will be easier to use that information and deal with it. And so you just try to reduce the number of terms in the most stupid way possible, and it works. And so this equation is solved. But important example, because we learned about the popularly known as cancellation trick. Here we learned about the triple involution trick. Is this example clear to everyone?
Yeah.
Yeah, clear as
Yes.
crystal.
Yes. Okay. Okay, I'm sorry, I had not read the chat in a while. Exactly. I just took this from Evan's handout. I had to because it's such a nice and important example. All right. Finally, an IMO problem. Uh, this one's actually fairly easy. I mean, it is pretty easy for its position. And first off, we are over the integers, so that's kind of cool. And then where we see the problem, the first. Oh wait, I should get started. Do you guys want a break or something, or should I just go to the next example?
No, no, go to the ammo problem.
Please give us 2 minutes for trying. Like
Okay,
to
yeah,
try
okay.
it.
I am so sorry. Please go ahead and try the problem.
Okay.
Okay, I guess enough people have tried the problem and probably solved it. So we'll just go with the solution really quickly. And like the moment you see the equation, you see that one of the sides has 2f and the other side does not have a, and by 2f I mean just mean f of f, and the left hand side does not have such a term. And so that sort of gives us the idea that maybe we could try to get rid of this double f, right? And so, how do we do it? And I mean, you could either think of it like this and motivate this, or you could just start plugging in numbers and it'll just, you'll stumble upon it in eventually. But the idea is simple, right? You just plug in a equal to 0. And oops, exactly. Right. And so a equal to 0 gives you f of 0 plus 2f of b equals f of b. Of course, in this equation, I could just write, instead of b, I could just write a plus b instead, right? That's just two variables, but it's still in integers, so that's totally fine. And so we get this, and this is the right-hand side of the original equation. So you can just now replace this one without any wrappings, and by wrappings, it just means without double wrappings. And so you could just have this equation to work with instead. A quick thing I'd like to say is usually when trying any functional equation problem, it's a really, really good idea to just try to find out the solutions before you actually try proving that they're the only ones, or just trying anything involving a proof. Just before that, really quickly, just spend some time, maybe just plug in ax plus b, or I mean cx plus d in this case, just plug in any linear function and see which ones work. Right. And now that we have this, like naturally, our guess is because this is an integer, we sort of believe that only linear functions of sorts should work. And so our goal is to prove that f is linear. Now, looking at these two terms, you see that this term has a 2 and this term has a 2, and then this is b, and you could just plug in a equal to 1 here, and then you get f of 2 times, or I don't need to write 2 times, I'll just write 2 times f of b plus 1 minus f of b equals f of, by plugging in a equal to 1, you get this, right? F of 2 minus f of 0. Just moving this term to this side and this to this side, right? And then what this really tells us is that the difference, oh wait, there is not enough. Right. And what this tells us is that the difference between two consecutive terms is constant. And as we already know, that implies linearity. And so you get that f is linear. And that's literally just it for this problem. I'll just leave the details to you guys to see which linear functions work. And that's really it. Once you prove that f is linear, the problem is done. And I mean, this was just a very silly example that you just want to simplify things as usual. And probably because it seems like the nicest thing to do to just get rid of these two double f's. And after that, you just plug in a equal to 1 and simplify the equation to get linearity. And that's that. This was just a very quick example, but it was just about having, I don't know, belief in ourselves and just proving the function is linear, because linearity is usually very nice. I'll just mention really quickly, or maybe, actually, never mind. Let's just, this example, I'm sorry, was really silly, but it was important and cool. And also because it's from the Aayam one. Who does not like Aayam problems? All right, this one is a far more interesting question. I like you, all of you guys, to try this and like give it your best shot. This is a really cool problem. All right then. The reason why I gave so much time for this problem is because I really, really, really wanted you to try it really nicely. Okay, I'd like to know really quickly if somebody would like to tell what they tried.
Yeah.
Yeah, please go ahead.
Like from observation, it is clear that f of x is equal to 1 by x is a solution.
Yes.
Yeah. So when we take proposition on x comma 1 by x,
Sorry, could you repeat?
setting y as 1 by x,
Okay, sure.
yeah, then we get f of x by x plus x square equal to f of x square plus 1 by x square. Now we see that if it is injective, then x square cancel and we get f of x. Just proving injectivity is right, and I was trying that only. And I tried different stuffs like plugging x as x by y, and then maybe plugging y as x by y to cancel some things.
Hmm.
Didn't happen.
Well,
And like
you
plugging y
did
as one.
say something correct towards the. I mean, all of what you said is correct, but you said something interesting towards the end, right? You said trying canceling stuff. Okay. Anyways, we'll just discuss the solution now, right? I was gonna blabber a lot, but I think it's pretty clear. If you just try plugging in random stuff, it's really not going to work out. Furthermore, this is over the positives, so it's gonna be even harder. And so, look, and obviously f is not linear as such and all that sort of stuff is hard, and so we've just learned one other thing. I mean, if you just try whatever we've learned so far, then by deduction you're only really left with one thing which we have learned but we have not tried here yet, and that is the cancellation trick. And what I mean is just blatantly setting this input equal to this input and seeing what happens. And I'll just type it up for you guys really quick. You get, I mean, if you just set them equal, and I'll just multiply it by y throughout as well, because obviously y is non-zero, so there is no issue with that. And so you get this, basically a cubic equation in y. Now, you could just shift all the terms to one side, but the main thing is if y is too big, then the right hand side is big, but if y is too small, then the left hand side is bigger because x can vary, right? And so you could just make y very, very, very small. And so basically, if you just consider this as a cubic polynomial in y, then one second, as this, right? If you just consider this as a cubic polynomial in y, then you see that by intermediate value theorem, or however you want to call it, this has a real solution and a positive one. All right. And so you can just take whatever value, let's just say y equal to k satisfies this equation. I mean, of course, it's just a lot of details and a lot of stuff that I'm saying. But what I've really done so far is just setting these two stuff equal and then just taking a y that satisfies this equation. And so let's just say y equal to k satisfies it. Then naturally, this term, what the equation that you get now is f of a, I'll just call it a. A is something arbitrary, we don't really care, and equals xk times f of a, right? Because we set the inputs equal. And then naturally nothing is zero, so you could just get rid of the f of a and you get xk equal to 1. Is it clear to everybody so far?
Yeah.
Yeah. And then basically now you have new information and you want to try and plug it in to this equation, and I'll just tell you, if you just use this and solve it, you get f of x equals 1 by x. End of story. That's literally it. You just take this and just plug it in here and you're done. That was literally it. This problem is extremely nice because of how you could try for ages and nothing would work. And the moment you realize that maybe I should try cancellation trick, And it's just done. The problem is done already. It's just that simple. And so it really shows how powerful the cancellation trick is. Which is why I,
Isn't there
yeah, go
isn't
ahead.
there a proof using injectivity? Like, can't we prove it injective?
Uh, None that I am aware of, unfortunately. The issue is, I mean, if you wanted to try and prove injectivity, the issue is still the same, right? You have everything is positive, and so getting actual equalities is going to be harder because you cannot really plug in zeros, even though you have free variables, which just makes it that much harder to get injectivity because you have squares here and you have this stuff here and everything is already positive. So getting any sort of such equalities, and if you look at it like f of x, suppose you wanted to plug in x equal to a, then you have a multiplier right beside it which cannot be zero, and so you just run into a whole lot of issues trying to just get injectivity, which is why at least I have been trying this problem. I gave up on injectivity pretty quickly because I realized it was way too hard. And as I said in the beginning, right, you always want to at least start out with the easiest stuff. Just try out the dumb stuff, like the really easy, obvious, and dumb stuff, and see what works. If nothing works, then naturally you'll have to start trying fancier stuff. But what if the dumb stuff just works, right? It's important to keep things simple, which is actually good advice for life too. But anyways, right. So keeping things simple, just trying out the cancellation trick, which is almost the most obvious thing here, because as I said, whatever we've learned so far, nothing really works, and so we see that cancellation trick might be a good option, and we try it, and it works, and the problem is solved, and that's it. That's it for this example. And before, okay, is everybody clear with this example?
Yeah. I want to ask one thing, like,
Yeah.
how much time should we try one approach?
Could you
कितने
please
time का?
repeat? Your voice is unclear.
Yeah, sorry. For how much time we should try one approach? Like after how much time we should switch to another one if we are not getting something useful?
Now, this is an interesting question. Like, if you're, it's not about time, it's more about if you feel like you're making progress. Like, if you're making slow and steady progress, then I'd say I don't know, try for as long as you want. But if you're not making progress or you're running around in circles or you're not getting any new information as such, then maybe it's a good idea to switch over. Like, let's say you spend 30 minutes without making any progress. And when I say without making any progress, I'm going to assume that you did not miss anything silly, right? And so if you go 30 minutes without making any progress, then definitely switch over and try
Like
something simpler usually.
it sometimes happens कि I am doing one approach, I switch
Mhm.
it, but when I see the solution, I see that my earlier approach worked. Means after not getting the second approach also, right?
Uh-huh.
It
Mhm.
usually happens with me.
Yeah, of course. That is something that would happen very often, and not just algebra. It would happen in many problems also check. It just happens. Sometimes what we try initially is supposed to work, but we just don't get it to work, and that's totally fine, right?
So actually, I joined a bit late now. So we equated the stuff.
Yeah, you just equated the. Sorry. What's the
I
name?
did that.
Right. I'm sorry, Pranav. I'm just interrupting for a second. Yes, we
Yeah.
just interrupted. Sorry, we just equated the inputs of f on both the sides, and then you get x times something equals 1, and then you use this information in this equation, and you get this. That's it. Short and easy. And cute. You could just actually, I mean, I don't know if that's your actual name. I'll just say, whoever this was, just try out what I just said and write out the details. And if something does not make sense, just ask me. All right? Right. And yeah, as I was saying, Pranav, this will happen often. Like this happens with me a lot. This will happen with everybody a lot because it's not possible to just be really good. And honestly, just doing that is expecting too much from yourself. And just try to have more fun than just solving the problem. All right?
All right. Thank you for this.
Mhm. Right. So is everybody else clear with this example? Should I move on now?
Yeah.
All right. Now, before actually going over to the next example, I'd like to just point out something interesting really quickly. Basically, this is again known as, even though, as I mentioned already, a lot of these things have the word trick in their name, even though they're not actually tricks and they're fairly motivated. Like by trick, you usually mean something that's like, oh, if you know this, you can solve it. If you don't know this, you cannot solve it. But whatever trick double quotes we've learned so far is not really a trick, right? All of that stuff is very motivated. Like you wanna the cancellation trick, you wanna reduce the number of terms, and then the triple involution trick, you're given some sort of information regarding iterations, and you want to use it in two different ways because naturally you want more information and equalities, and so even that is very motivated as well. And so I'm kind of sad that this stuff is called tricks, but whatever. Right. And so this one now that we're going to look at is called the symmetry tricky or symmetry trick, whatever you want to call it. And the reason and the motivation here is actually probably the easiest to understand and see. What happens is oftentimes you're given some equation where a few of the terms are symmetric in the variables. What do I mean by that? Like for example, f of x plus y. This term does not, this term treats the same, treats x and y the same, right? And then you have f of xy. And basically the variables are same. Like what I mean here is if I swapped x and y in this, right, that would just be by x, but multiplication. So it's still the same thing. If I swapped x and y here, I'll still get the same thing, right? Because addition is commutative, right?
Yeah,
Hello.
yeah,
Right. And so why would we want to look at this? Like sometimes you have a few symmetric terms and a few of them are asymmetric. Like I'll just type up this silly equation really quick. It's a very artificial equation. I'm just making it up. So I don't know if there are any solutions or not, but it's just to illustrate my point. Right? Like if you look at this equation, you see that the left-hand side is symmetric, but the right-hand side, one second, I'll just let it render. Right. You see that the left-hand side is symmetric. As I already said, symmetric just means nothing would change if I swap the variables around, right? Like if I had replaced x by y and y by x, nothing would change. And so the left-hand side, or at least these two terms, are completely symmetric. And the right-hand side is not. And then you want to know, right, what's the reason for this asymmetry? And why do we have symmetry on one side and why do we not have it on the other side? And so to do that, you just, what's the easiest way to do it? Like, or at least to gain some information out of this structure is to just swap the variables, right? And so if I just swapped x and y, I would get f of 2y plus fx equal to the same thing, which is this. Right, I just swapped x and y around in this entire equation, like I replaced x by y and y by x. And the middle term will stay the same, and you get this on one side and you get this on one side. Right, so essentially, after all these words, the core idea is still very natural and motivated. You have some symmetry and you have some bumps in symmetry or asymmetry, and you want to exploit this structure to get some more information out of it. You want to exploit this relation of symmetry and asymmetry and get information and equalities out of it. And that's really just it. Now, just from this equation, we get this. I mean, this was just a silly example, silly and artificial example. So there is no actual point to it, but just to illustrate the point. All right. Now, after the
yeah,
knowledge of symmetry tricky, we'll just head over to this problem. First off, as I had said before, it's good to just have a guess for the solution before starting. Actually, I'll
yeah. I
just let
want to ask
yeah,
something in
yeah.
this.
Please go ahead. Please go ahead.
Here the power means ki f is being repeating that much times, or f
Yes.
of z to the power is that.
No, it's
मतलब,
okay. Okay, I get what you're trying to say. I'll just explain it. If it had said f of z to the k, then that would have meant, oops, where did it go? Right. Then this would have meant f of z k times, all right? This is
Yeah.
with the regular part. This is just the regular part, right? But if it says f to the k of z, then that means f of z. Like applying f that many times,
No.
right? Is this
Yeah.
clear now?
Understood. Yeah. Yeah. Understood.
And so now I'd like you guys to try this problem. But once again, just because I mentioned the symmetry tricky right before starting this problem, I don't want you guys to streamline your thinking and only try to somehow. I mean, I don't want you guys to try to force the symmetric trick into working on this problem. I want you guys to try this problem like you normally would try any functional equation problem. All right? Yeah, please give this one a shot. Okay, right. So as I said before, I clarified that you guys should probably write this properly freely and not just streamline your thinking involving symmetrically, right? This was important because now the reason why I had mentioned the word, when we were discussing, if you just scroll back up, when we learned the triple involution trick, I said the word iteration, and I had only used the actual term triple involution once because, of course, this does not just restrain to two iterations, right? You could have as many iterations as you want, and that's exactly what's happening here. Like if you replace z by fz, then you get. I'm just gonna copy this real quick. Right, and so if you replace z by f of z, first off you get this, and also if you replace if you just take off the f of the entire thing, you get this. Right? Does everybody agree with this?
Yeah.
Yeah, okay, nice. And so now you naturally have that these two terms must be equal. Right. Right.
Why is there a 1 in the first equation?
Because you just what I had done is just I had applied another iteration, right? I know this is a bit notationally heavy, but just if you
Okay,
think
okay.
about it carefully, I just applied f
No,
once
no.
more. So yeah,
Understand, understand.
okay, great, great, great. That's actually amazing. Right. Actually, this f right. And so you get this right because the left hand side, as usual, basically just this triple involution trick, except triple if you remove the triple out of it. So involution trick. So let's just call it that. And so this and this, these two are equal, so you get that these two are equal. Now coming back to what I had said right before this problem, you see that the left hand side is symmetric in x and y and z, but the right hand side is not. And so we want to know the reason for this, right? We want to know why this is happening. And so naturally, if you swap x and y, you're not going to get anything out of it, but you may as well swap x and z now. And that would actually, I'm just going to edit this equation right here, and that would give you f of, this term is going to stay the same, right? Because addition is commutative. So if you swap x and z, this is going to be the same. But then you get f of x plus y plus z plus 1. What you have is f of x plus y plus z plus 1 equals f of z plus y plus x plus 1. And so obviously the y plus 1 cancel out on both sides and you get f of x plus z equals f of z plus x. Right? Are we clear on this? We just swapped x and z because, as I said, this term is symmetric in x, y, z.
Yeah.
It is not differentiating between x, y, and z, but this side is. And so you just swap x and z because obviously swapping x and y does not do anything. You know, once you see this symmetry, you want to know, you already know that you want to swap something, but x and y does nothing, so you just swap x and z instead. You could have also swapped y and z instead, but who actually likes y as a variable? Right? And so y plus 1, y plus 1, y plus 1, y plus 1, they cancel out and you get this. Obviously, now this, if you just rewrite this, you'll get f of x minus x equals f of z minus z. And just once again, enough to imply that f is linear. Do you see why this is so?
Yeah.
Right, because if you just fix some z equal to z naught, fix it and never change it, let's just call it m. Well, actually, let's just call it capital Z. Then you get that f of x, sorry, f of x equals c plus x, just transposing that c to the other side. And so f is constant. F is linear, my bad, f is linear. Right? And after you have this, then it's just You just plug this into the original equation and you expand, and it's just a bit of the size thingy. You could do it by AMGM or whatever you want to do it with, and you basically obtain that C should be 1. Otherwise, equality won't go. And that solves this problem. So the solution is f of x equals x plus 1. And that's it. And this problem was so easy. Initially, I had struggled on it for a lot of time, but once I realized what's going on, then it died almost immediately. Because again, now I'll try to motivate what we just did. Like first off, we see a bunch of iterations, and so the first thing that comes to mind is trying to exploit this relation, right? Because you could increase the input by 1, increase the input. What I mean is increase the iterations by altering the input, or you could just take f once more, and so you do that basically triple involution trick. Seeing iteration basically motivates or demands, actually, it's just it demands triple involution trick. And you do that and you get this information. And then you see that there is some symmetry here, but no symmetry. There is no direct symmetry here. And you want to know the reason for that. And so you swap two variables and you see what happens. And what happens is you get this equation out of this. And then stuff cancels and you get this. After that, it's pretty trivial that f is linear. And now the rest of it is not actually functional equation stuff, right? The rest of it is just size and number theory stuff. It's not actually number theory, it's just size stuff. So I'm just going to ignore that. But the main part of this problem was, in fact, triple involution and symmetric tricky. Is everybody clear now?
Yeah. Also, sir, by seeing that problem, it was initially also very symmetric.
Initially, also very
Symmetric it seemed to be. That
yes.
did.
Which is, and in fact, you're absolutely correct. Initially, the right hand side is still completely symmetric, but the left hand side is not. And so that is exactly why I had said to not streamline your thinking. Because if you had done so, then you would have seen, sir just mentioned the symmetry tricky, and the right hand side is symmetric, so I should try swapping variables. And you would have been stuck there, which is not the right way to start, right? The right way to start is to keep your mind open, look at the iterations, and then you think of the involution trick. Does this make sense?
Yeah.
Right?
Yeah.
Does this make sense to everyone? Is everybody clear? Could we have found something? Right. Actually, I had actually mentioned this already. If you swapped x and y here, because of course, this term would still stay the same, but both of x and y are outside of f, right? There is this z which is inside the f, and x and y are outside the f. So if you swap those, you won't really get anything new. It would just be y plus x, which is still the same thing. And so we want to get this z out and that x in to get some new information. That's that. Which is why you swap x and z. As I said, you could have also swapped y and z, and that would have given you the same thing because z is inside. So you definitely want to swap z, and then yz or xz, whatever you like. But we have that would have been hard, and honestly, I've never actually tried that. I had tried that initially. Actually, that did not get me far. As I said, right, initially I had tried and failed for a long time before realizing what's going on. So when I had tried this problem, I had tried something similar too, and a lot of complicated stuff, none of which works out. And so, yeah, that's your answer. It's a lot more complicated, and keeping things simple, as I've said already, is almost always a best bet. All right. All right. Did that example make sense to everyone?
Yes, sir.
Yes. And you see, in almost all these solutions, what I'm trying to do is instead of actually going over all the details, I'm trying to motivate you. Like, I'm trying to show you why I tried or why we are trying what we are trying. We get these hints and cues from the equation, right? And we try to understand those hints and cues and base our actions or substitutions or any form of analysis or whatever based on those hints and cues. So we are not doing just random plug and chug. They're actually doing, let's say, educated plug and chug, and they're taking educated decisions. which is what will help you solve faster, right? All right. This example, this is this is actually quite a okay. No, actually, we'll do it anyways, right? Um, all right then. Do you guys want a break or something now, or should we just continue over?
As you're comfortable with.
Huh?
As you're comfortable.
No, actually, I'm comfortable with anything, right? But you guys are here to learn. I already know all of this stuff. Your convenience is more important here.
We are fine. We can manage. I think.
Fine then. I mean, I guess you guys are fine with staying, so we'll just try this example. Just try this example for 5 minutes really quick and get a feel for it, and then we'll discuss it. This one's rather quick, actually.
It was a great session. Looking forward for the next session.